questions? Let's then move on to Chapter 11. First, let's just talk about a few things that motivate why we might be interested in three-phase power. One, did anyone or has anyone worked for a power company? So there's a few hands. Those companies are interested in moving large blocks of power, not just something to supply a few homes here and there. They need to move a lot of power easily back and forth. And three-phase power allows us to do that. And one way that the three-phase does that is with high voltages. And in fact, we can obtain these high voltages since we are dealing with alternating current or with AC using transformers, which are really just sort of a passive device, a bunch of coils, right? Have you guys built transformers, or did you in 220 with a iron core and a couple of windings? Now those work by this alternating current mechanism, don't they? And you could step up the voltage, you could step down the voltage, and you talked about the transformer relationships, I think, and the dot convention. Is any of this starting to sound familiar? Well, you can use those to build up or boost your voltage. So you can obtain high voltages using transformers when this voltage is going back and forth, or when it's AC. Versus if you were dealing with big DC installations, you might need to use rotating machines, and that might be more expensive or more complex than a passive transformer. Versus, let's say, using rotating machines to raise and lower. We need to actually drop those voltages down because you don't have thousands of volts coming into your house, do you? Hopefully not. Not intentionally. You might if you have a lightning strike, right? Anybody been hit by lightning? Not physically, but your home? Yeah, it's pretty common here, isn't it? Kills a lot of things. Microwaves, routers, TVs, garage door openers. Yeah, a lot of things. And lower voltage for DC voltage. So that means that with AC, which is what we've been doing in Chapter 10, now we'll do it again in Chapter 11, that allows us to have less complex systems for growing and subtracting, or let's say, for raising and lowering voltage. What are some other reasons for dealing with three-phase power? If you, I should have done this in green, huh? There's economic reasons. If you're transmitting the same amount of power with single phase or with three phase, you can, I hope, appreciate the fact that the lines don't have to carry as much current if you split it 3 ways. So now you can have smaller lines, or physically smaller lines in diameter and dimension when you're dealing with 3-phase to do the same amount of power transmission. So we have economic. We have smaller or lighter components than in single-phase, let's say, systems or networks. And another maybe bigger reason, as engineers, we have to worry about a lot of things, don't we? Yes, sir. So now smaller and lighter, if you had to, let's say, transmit, so the question was, where did this smaller, lighter come from? If you now needed to put, let's say, 10 amps down a wire, well, if I want to transmit that same 10 amps, but I'm allowed to split it 3 different ways, then I can divide 10 by 3 effectively. That's the crude way of thinking about it. So these lines don't have to carry the capacity of current, the same magnitude of current. So now these lines are lighter physically than a big one that has to carry 10 amps. Does that help? So now we're splitting things up. We have 3 phases instead of just 1. So that's economic, but performance-wise, you can show that if you're looking at machines, if you now have those machines and they're 3-phase machines, you have an A phase, a B phase, and a C phase, then you are going to have a much steadier torque being delivered to that machine or being received by that machine. Because now you're going high-low, and then you go high-low, then high-low, instead of high-low. Is that making sense? So you have a steady torque. That's why I'm not in the fine arts area of campus. Somebody laughed at my high and low. Steady torque supplied to machines. Which can reduce the vibrations and make this delivery or consumption more efficient. Now we are going to concentrate mostly on balanced 3-phase. What that means is everything in the A phase impedance-wise looks the same as everything in the B phase, as everything in the C phase. All 3 phases look the same in terms of what the load presents to the system, what the transmission presents to the system, what the generator looks like, and we will concentrate on having balanced voltage supplies or sources. So we will look at balanced 3-phase power, and there's an economic reason for having a system balanced. And that will become a little bit more clear when we start drawing the way these systems are interconnected. But one of the big economic reasons is there's no current flowing in the neutral conductor. And if there's no current flowing in the neutral conductor, there's no power loss. And so we save money. Don't have to worry about that expense. So no power lost in the neutral conductor. That's if we have balanced configurations or a balanced system. Everything's nice. Now we have no power or no current flowing in that neutral. Also, if we understand how to analyze balanced three-phase power, we can actually use that to understand how to analyze unbalanced circuits. So some unbalanced circuits or conditions can be solved by what are called symmetrical components. That's balanced in our terminology. And symmetrical components is actually based on or relies on an understanding of balanced operation. So this relies on understanding balanced operation. There was a lot of green in there, wasn't there? There were a lot of economic reasons for looking at three-phase. We had maybe less massive size of components or hardware. We maybe aren't losing power in the neutral conductor. It's easier to analyze if we're dealing with balanced three-phase systems. Let's now look at what this might look like in a very high-level block diagram form. Here's a block diagram of a three-phase system. We have a three-phase source. That makes sense. Well, that's going to then be maybe the voltage level at the source is not as high as we want to go across the country or go across part of the country. We may want to step it up, raise that voltage level, so we may have to have some transformers. And then those might then, that high voltage is going to go through transmission lines. So here's some transformers. And on the other end, we need the transformers to step that voltage down. So all of this in the middle with transformers and transmission lines is another part of this block diagram. And if we have a three-phase system, we have at least 3 wires, and we may have a neutral wire connecting the source with this transformers and transmission line interconnected system. And finally then, over on the right is we have our three-phase load. And again, it has the 3 phases and maybe a neutral conductor, maybe. In this class, I'm assuming that you've already played with transformers in 220. So this guy, we're not going to worry too much about. So for all you texters, log. Is that okay? Without loss of generality. That wasn't obvious? I text that all the time. Where are you going? Without loss of generality, WLOG. So this is, we're not going to worry about the transformers, okay? We may sometimes deal with transmission lines. Sometimes we may just worry about sources and the loads and skip the transmission lines. And the transmission lines will just present us with impedance and reactance. So we may just say, for now, let's just assume that's minimal in some problems or in some cases. Now, what we want to do is talk about the different types of pieces in those blocks. We've just thrown one away. Without loss of generality, we're going to forget the transformers. But let's look at the sources. And those are typically going to be voltage sources. And like I said before, let's just concentrate on looking at balanced systems to begin with. We now have 3 voltages to worry about. Let's draw one voltage here, and I'll call that V sub A. So V sub A is a phasor. It has some magnitude. Let me just say that's V sub M. Because it's balanced, I want all the magnitudes of each phase to be equal. And this one, what's the angle of V sub A relative to the horizontal to the right? That's 0 degrees. So now this is going to be my A phase, since it was subscripted A. That's my A phase voltage. And now to be balanced, I need these phases to symmetrically divide a circle. So I need 3 lines symmetrically dividing a circle. A circle is how many degrees? 360. Easy, right? So now we just need to divide that by 3, and that gives us the angle, the 3 angles between these voltages. The B voltage, and this should be the same length, you now know what angle it needs to be. What's that angle? That's 120 degrees. So that now V sub B, the B phase, has the same magnitude, but it's now at minus 120 degrees. And that's the B phase. And then we have the A phase, which is 120 degrees from that. What did I say? This should be the C phase. So that's V sub C bar, and that has the same magnitude, but now convention is we usually keep our angles between 0 and 180 in terms of magnitude. So that one we could say is at plus 120 degrees, or minus 240. It's exactly the same location. Here is our C phase. And this particular interconnection of voltage sources is referred to as a positive phase sequence. If you were looking at omega, which omega is implicitly shown, it's really not there, but omega, the frequency, causes these phasors to be spinning counterclockwise, is the positive direction. So if I'm standing up here in, let's say, the first quadrant, and I look at these voltage phasors as they're circulating around me, what's the pattern that I see? I see the A phase. Then what do I see? B. Then C. So that's the positive phase sequence, A, B, C, A, B, C. If I was observing that from, let's say, right here, oh, now you'll know why I'm definitely not in the fine arts area. But there I'm observing. That's an I. Don't laugh. And these are going this way, aren't they? And if they are, then this is a positive phase sequence. Or somebody may just say the ABC phase sequence, or they may just say the ABC sequence. And if you forget, you could say, well, if I was learning my ABCs and I wanted a positive answer or a positive mark on my paper, I better say ABC, right? That's the positive phase sequence, and if you just know that they're going counterclockwise, you know where to draw them. The other phase sequence is the negative phase sequence. Or the Acb phase sequence. In this case, we have the A phase here. Now we have the C phase there and the B phase here. So that V sub A is again V sub M at 0 degrees, V sub C, or maybe I should say V sub B, since we could do it that way, is V sub M at 120 degrees, and V sub C is V sub M at minus 120 degrees. Questions on those phase sequences, and those are supposed to be vectors of the same length or magnitude if they're balanced. So if we have a balanced phase sequence, we have to have the vectors of the same length, and then they're just separated by 120 degrees. And whether you have an ABC or an ACB, you just need to be told. Because if you're now interconnecting systems, you need to know what phase sequence you have. You don't want to put a positive phase sequence and a negative phase sequence together. That's a bad idea. You need to only combine things with the same sequence. Circuits, then, let me say, can operate in parallel only if they have the same phase sequence. Now, here's a quiz. Do we have to turn it in? You know the answer, right? So now, here's your quiz. What is, if I add up V sub A vector with V sub B with vector V sub C? So now I'm adding up V sub A, take the tail of V sub B and put that on the tip of V sub A, then go to the tip of V sub B and add the tail of V sub C. And what happens? If we have a balanced system, which means these vectors are the same length and they're 120 degrees apart, zero, isn't it? And those represent phasor quantities. What about V sub A of t, the instantaneous? If you added up all of those phases, what would happen? These are now instantaneous. So let me say what's that going to do? Pardon? It's zero also, isn't it? Because now those phasors we can put into cosine waveforms. They have the same magnitude, those angles, the omegas are the same. We're going to end up with that being zero for all time. And that's going to be helpful in understanding what's happening with respect to these systems. Now, we have these different sequences. We can also interconnect these sources or voltage sources in two different ways. Two ways to wire three-phase voltage sources. The first way is to put all of their negative terminals together. And then we might say, okay, here is V sub A, here is V sub B, and here is V sub C. And those could be a positive phase sequence or a negative phase sequence. But they would be wired up in this configuration. Yes? Pardon? No, the question was, does this only apply if they're balanced? We will interconnect these, and our system could be unbalanced or it could be balanced. We're going to concentrate on balanced, but you could still have this interconnection for an unbalanced system. This, can you anticipate what this connection is called? The Y. It's upside down, but if you just look, if you stand on your head, it looks like a Y. If you, oh, I was going to cover this up. That helps you a lot, doesn't it? And I'm not quite tall enough to do it there. But if you look at this, that looks sort of like a Y if you flipped it upside, right side up. So there, this is our Y. And it's what a 2-year-old would like, or a 3-year-old. Y, Y. So this is a Y connection. And this is then our A terminal, this is our B terminal, and this is our C terminal. And it might be that you would have actually a neutral conductor. You may or may not. But what you may have access to, you may not even know what's going on behind those terminals that I'm sort of highlighting in blue. You may just have 3 terminals, an A, B, and a C. And you're told, okay, here's your voltage source, and it's a positive phase sequence. Have fun. And then you have to figure out how to analyze that. And we're going to be talking about different kinds of currents and voltages. Let me give you the next interconnection. I've already told you the answer, so now if you remembered what we said we would consider at the end of the class, now we have the second wiring diagram. And these are connected more like head to toe, or toe to head. So this is now where this might be our A phase voltage, this might be our B phase voltage, and this is now our C phase voltage. So that this guy would be the A terminal, this would be our B terminal, and this coming out of the positive of the C phase is our C phase terminal. And again, if you highlighted this in a blue highlighted, you couldn't tell this one from the other one, interconnected wise. But this is referred to as the delta connection. And what we are going to be talking about subsequent to this are different kinds of voltages and currents. we are going to have two different types of voltages and currents. We're going to have a phase and a line, and that will become a little bit more clear as we go, I hope. But what I haven't included here, which I could have introduced, let's say right here, and then right here and right here, is I didn't introduce any impedance, did I? But it's a machine, it's going to have some impedance. Sometimes we will neglect that and sometimes we won't. But in the above configurations, I've drawn those without generator impedances, but they would go in that blue highlight that I've indicated in the delta configuration, and likewise in the Y. Yes? So now, where would the neutral line come in this delta configuration? Doesn't exist, does it? So now you don't have a neutral in this configuration. It doesn't happen. There is no neutral. Okay? Good question. It's not there. And it's not there because it can't be there. It's not because I left it off, which that's a good reason to ask the question. Hey, did you leave something out of that diagram? I can't put it anywhere, right? There's no neutral for those three voltages. But the impedances on the generator then, we would lump them all into two different pieces. We might have winding resistance. We have a lot of coiled wire inside generators and machines, and that wire just has an inherent resistance to it. And if we do have coils, then we're going to have these reactive pieces, this inductive reactance. Now, that was the sources. Remember our big block diagram, wherever that was? Now we've done the left-hand side, and that could be either Y connected or delta connected. Now we'd have transmission lines feeding our load, and the loads, they can be connected either way, Y or delta. So we might have a load that looks like a Y connected load. What would that look like? Well, that could look like this, where this might be Z sub A, Z sub B, and Z sub C. And you know what, when we get to the load side, we usually try to distinguish that with capital letters. Hopefully I'll be somewhat consistent. And not make too many mistakes. But that would be a Y-connected load. And a delta-connected load and if it's balanced, what do you expect will happen? Maybe I should have drawn those with uppercase. The C's are hard to tell, but if it's balanced, all of those impedances should look or be equal. So here's our Y, and here's our delta for loads. And those ABC terminals can go with the ABC terminals of either a Y-connected source or a delta-connected source. Here's our math combinatorics problem. How many possible configurations or arrangements do we have? We have 2 at the source, 2 at the load. We have 4 combinations, don't we? So we have 4 possible arrangements of sources and loads. We could have a Y-connected source with a Y-connected load. We could have a Y-connected source and a delta load. We could have delta-connected source with a Y load, or we could have a delta-delta. And so you'll hear me saying things like, consider a YY connection, or consider a Y-delta configuration. The first one is the source, the second one is the load. Questions on those combinations? So if that's the case, let's see if we can actually sketch a YY three-phase circuit. Now, really get out your sketching ability. Here is our source. Maybe that's the A phase, and I'm going to label that as an A prime, and I will actually put my generator impedance here as Z sub GA, and then that goes out to this A terminal here. Then I might have a load a transmission line impedance. That's supposed to be Z sub L of A. That comes out here to the A terminal side of our load. There's Z sub capital A, and then here is capital N. Maybe I went too far down, but let me call that little n. Then I have my B phase with its generator impedance, its transmission line impedance, and its load impedance. So let me move that neutral up. And finally, so this one was now, this should be my A prime N. This is now V B prime N, where this point is B prime. And I have one more thing to worry about. In this YY configuration, I can actually introduce a neutral conductor. I can now have a line between the two neutrals. And in between those, I could label that as having some impedance on that line connecting the two neutrals. What I haven't done is introduce any currents, and I can label those. I can have a current here in the A phase, and this would be I sub little a capital A going from little a to capital A. I sub AA. I sub BB, where that was clear that that was lowercase b, uppercase b when I said BB. Hard to tell, huh? And this is now I sub CC. And I have a current flowing in the neutral potentially. And now all of these, whoops, these are phasors. The A prime N, the V sub B prime N, the V sub C prime N, that's now a balanced set of voltages. It could be a positive phase sequence or a negative phase sequence, but this is now a Y configuration. Does that make sense? Yes. So now the question was, where did this notation come from? I think, on the sources. So now I'm referencing the first subscript is the more positive terminal, and the second subscript is relative to where the other end of that or the other side of that is, and that's coming to the neutral terminal inside the Y-connected source. So the V sub A prime N is between terminals A prime and N. If I did not have any, if I neglected the impedance in my generator, then I wouldn't have that Z sub GA, I wouldn't have the Z sub GB, and I wouldn't have the Z sub GC, and the C prime and the C would be the same, right? Or I might neglect the transmission line impedances. Maybe I keep the generator impedance and I keep the load impedance, but you can see how now I have this system. Now I can talk about different pieces of that system. One thing that I can talk about, and this is going to take some getting used to, is I can talk about a phase voltage and a line voltage, and I can talk about a phase current and a line current. And they may or may not be the same, and it depends on the configuration. So when I speak of phase, that pertains to the specific phase. For example, in this case, if I said, I want to know what is the A phase current at the load, then I would be referring to the, what did I say? Did I say current or voltage? That's what I thought, and I labeled it as a voltage. Let's talk about the phase voltage on the A phase. The A phase voltage would be the voltage between terminal capital A and the neutral. If I said, what's the line voltage? Well, the line voltage is actually transmission line to transmission line, which means now I would maybe take my ohm meter and measure the voltage between capital A and capital B. And that line voltage is different from the phase voltage. Is that making sense? I also can talk about line current and phase current. In this configuration, in a Y configuration, they're equal. My A phase current is the same as that line current. The transmission line current is I sub little a capital A. We'll get more into that next week. Have a good weekend.